Good evening, everyone. This is your session number 10 related to structure analysis tools. So, what we used to do in these sessions, we used to solve all the problems related to the topics what you have covered in the ongoing week. So, till now, we have covered half of the part of the analysis of indeterminate structures, wherein we have seen the problems related to trusses, how we have solved that. We have solved using method of consistent deformations. Then we have solved the problems related to beams, whether it is of first degree or when you have continuous beam. So at that time we have used three moment theorem, and for 1 degree indeterminacy we have used force methods. So today we will solve some problems related to beams and frames using stiffness method. So let me share my screen first, then we will see how we can solve the problems related to stiffness method. I hope the screen will be visible to everyone. So let's start this session. So this is your week number 10, which we conduct every week on Saturdays. So this is a problem solving session wherein you will solve the problem related to topics which you have covered in the ongoing week. So introducing myself, my name is Pranam Mahajan. I am a PMRF scholar in Department of Civil Engineering and IIT Madras. So we are given this opportunity by NPTEL to help you in understanding the concepts and the significant problems that you encounter during the solving of assignments, and helps you in clearing the doubt regarding the same and let you having a better understanding of the concept of the topics you have covered till now. So in case you have any doubts, you can ask in between the class or also after the class in the discussion forum in the Swayam portal. So talking about the course layout, we have completed week number 10. That means only 2 weeks are remaining for the completion of this course. So till now what we have covered, we started with the analysis of determinate structures, but before that we have seen how you can determine shear force and bending moment diagram of different structures, whether it is beam, whether it is a frame, how you determine under different loading condition with different boundary condition that is provided to you. We have seen the determination of shear force as well as the bending moment diagram. Then we have seen then how we can determine the degree of static indeterminacy as well as degree of kinematic indeterminacy, or you can tell it as degree of freedom. So for trusses also we have seen how we can solve for indeterminate structures. So we can solve that using method of joints and method of sections. And when you are expected to determine the horizontal or vertical deflections, then at that time you can use method of virtual work. Whereas when you are solving for beams and frames, we have different methods available. You can use moment area method, conjugate beam method, virtual work method, direct integration method, and unit load method also. After that, we have seen how you can solve the problems related to moving load, wherein we have seen the effect of influence line diagram and the Mueller-Bridge law principle on the moving loads. Then we have seen where the maximum shear force and maximum bending moment occur in pertainment to the proportioning of the loads that are there in the section. After week number 6, we have moved to the week number 7, wherein we have started with the problems related to the indeterminate structures. So the problem will remain same. That means your structures will remain same, but now it shifted from static determinate to static indeterminate structures. So in this, we have seen the introduction of two methods. One is force method, which you call it as flexibility matrix or flexibility method. Another is stiffness method, which you also known as displacement method. So for this, we have seen how to solve the problem related to trusses. We have seen the method of consistent deformations. Then for beams and frames, we have seen how we can utilize the force method and the three moment theorem till now. So today what we will cover, we will see how you can solve the problems using stiffness method in the indeterminate structures. So let's start this session by solving few problems related to this, and it will help you in clear understanding of the concepts related to stiffness method. So in week number 10, you have done the analysis of indeterminate structures using displacement method. So all the videos are there on the NPTEL portal. You can visit whenever you want and try to gain some knowledge from that, and then try to solve the assignment and the questions which are related to stiffness method or displacement method. So first, what are the different types of displacement methods? So in displacement method, let me write. In displacement method, unknowns are displacement instead of forces. Okay. So earlier you have determined the forces under different conditions using force method. So in your displacement method, you have the displacement as your unknown. Okay. So what are the different types of displacement methods? So different types of stiffness methods includes the following. Okay, so your first one is slope deflection method. Your second method in this is moment distribution method. The third method, which comes under displacement method, is Carney's method. The fourth method, which comes under this, is stiffness matrix method. And the last method, which comes under this, is Castigliano's theorem first. Okay, so these are the methods by which you can solve all the problems related to displacement methods. So you can use any method, but depending upon the type and the complexity of problems, whatever will become easier to solve any problem, we will use that method to solve and determine the unknowns, which are displacement in this case. Okay, so let's start and solve few problems related to this. So in this, the first problem is a clockwise moment of 70 kilonewton per meter is applied at point B of the following frame. Then what will be the rotation at the rotation at the end B? Okay, so due to the application of the load, or you can say moment in this question, you are expected to calculate the rotation at the end B. So to determine the rotation at the end B, first we will determine the rotation stiffnesses. Okay, so in that we have seen that when you have hinge at the far end, so if you see the span BC, your far end is support C. So in that case, your hinge is the far end condition. Okay, so by that, in the span BC, let me write. So for span C or for span BC, free end have hinge support. So in this condition, your rotational stiffness, how you define rotational stiffness? It is the amount of stiffness that is required to produce unit rotation. Okay, that is how you will define the rotational stiffness. So your rotational stiffness will become equal to 3EI upon length of BC member. Okay, so that will be equal to 3EI upon 2 equal to 1.5 EI. Further, it is also connected to span AB. So for span AB, your far end condition is I have written free end now. It is far end. That's why I got confused here. So this is your far end. Okay. So your far end is having hinge support. In this case, your far end is having pitch support. So when you have pitch support at the far end, your rotational stiffness is defined as 4EI by L. Okay, but in this case, your E is twice EI. Okay, divided by length of AB. That will become equal to 8 EI divided by what will the length of the member is 4, and that will be equal to twice of EI. So your total rotational stiffness, is equal to the sum of the rotational stiffness of span AB and span BC. That means twice of EI plus 1.5 times of EI. And that will be equal to 3.5 times of EI. Now, as I already told you that stiffness, or you can say rotational stiffness, is how much moment is provided to produce unit rotation. Okay, that means your theta B will become m upon 3.5 EI. Fine. Okay. So in this case, what is your M? It is 70 divided by 3.5 EI. If you solve that, you will get to be equal to 20 upon EI. Fine. Okay. So this is your theta B. Now we will go to the next question. So your next question is, if the propped end of the propped cantilever beam having length L and constant EI settles by delta, that is your displacement, then what will be the vertical reaction induced in the fixed end? So let me draw first how the propped cantilever beam looks like. So this is your propped cantilever beam. Okay, it is having roller support at one end and fixed support at the other end. Okay, in the question it is told you that it will have an settlement of delta. So how it will look like? Let me make it. Okay, so this is how your settlement profile of the beam will look like, and it is displaced by delta. So this is your settlement delta. Okay, that means your support gets shifted here like this. Now that means some force might be have applied in this direction to produce a settlement. So let's say if we tell it to be a clockwise moment, let me tell you it to be a clockwise moment of how much? 6 EI upon L square. So this much moment is provided to produce a settlement of delta. Okay, that means to keep the beam at 0, another moment will also come into picture, that is at the fixed support also some moment will be applied, that will be equal to same value 6 EI upon L square. Fine. Now as, let me write, this is your end A, this is your end B, as roller support B have certain moment, let me write in this way, as support B have roller, therefore moment at support B should be equal to 0. You have seen previously also that if your end is hinge or roller, that means no moment should be there at that particular point, correct? That means if you have an applied anti-clockwise moment in the roller support To counter it, you need to apply a clockwise moment of the same magnitude. That means we have to apply the same moment of 6 EI by L square to make the moment at the roller support to be equal to 0. Then corresponding to it, you will be having a carryover moment at the free end, which will be the half of the applied moment. So it will give you a same direction moment at the fifth support to be equal to 3 EI by L square. If you add both of these moments, let me write, summing up all the moments, so your moment at fifth end came out to be equal to anti-clockwise having a value of 3 EI by L square, and your moment at end B, what is the value? It is equal to 0, which is actually the same as per the conditions that are provided on the boundary supports. Okay, so that means this is your moment. So if there is a displacement of delta, then you will be having the total moment to be equal to 6 EI delta, and same moment will come into picture, and their corresponding carryover moment will become 6 EI delta upon L square, and its carryover moment will come out as 3 EI by delta L square. And finally, it's summing up, it come out to be 3 EI delta upon L square. Fine. Now we have one reaction here, also RB. If we take summation of moment about A to be equal to 0, it will give you RB into L to be equal to 3 EI delta upon L square. From this, if you need to calculate the unknown reaction RB, it will come out as 3 EI delta upon L cube. So this is how you will calculate unknown reactions in case you have settlement in the cantilever being subjected to a prop support. Okay, so let's solve one more problem. Now your next question says you have a clockwise moment is applied at the prop support end of a prop cantilever beam to produce a unit rotation at the free end. Okay, so that means due to the application of clockwise moment M, a unit rotation is produced at that end. Now you have to determine what will be the value of this clockwise movement. As I already told you, how you define the rotational stiffness. It is the amount of moment that is applied to produce unit rotation. Okay, so in this case, your M will become your rotational stiffness because theta in this case is equal to 1. Fine. So let's draw the diagram, then it will be easy for you to understand it. So Again, we will make one prop cantilever beam having roller support at one end and fixed support at another end. Let's mark it to be equal to A and B. It is having length L and modulus of rigidity, modulus of elasticity to be equal to EI. Okay, so a clockwise moment is also applied at the free end. Let me mark it as this, and it has a value of M. And due to this, how the beam will rotate? It will produce a Hodgin moment. Okay, so let's draw the deflection profile. So its deflection profile will be something like this. Fine. And how much will be the rotation it will be observing? So the rotation in this, if I try to mark it, so in this case, the theta b, this angle, your theta b is equal to 1. Okay, so let's first divide this problem into two parts. Then it will be easy for you to understand. That means we are making the reverse of the superposition principle. So how we can divide it? So let me write it to be equal to, I can make it to be equal to one cantilever beam subjected to a clockwise moment at the free end like this. It is having a length L. Okay, plus what we can make? We can make another cantilever beam which is having a concentrated load at the free end like this. Okay, so I am dividing the original problem into two parts. Now you have one clockwise moment M and one reaction due to the roller support equal to RB, and it has length L and modulus of elasticity to be equal to EI. Okay, so let me write it to be case A. So this is your case A and this is your case B. Okay, so for case A, your theta BA or your theta B1, how you define it? To be equal to ML upon EI. So these are the standard results that we have seen in moment area method as well as conjugate beam method. How we get that? Okay, and similarly, your delta B1 in this case will become ML square divided by 2EI. I hope till this point everything is fine. Similarly, for case B, we have theta B2 to be equal to RB L square. So your theta B2 will become RB L square upon 2EI. And similarly, here your delta B2 That means your displacement will become RB L cube divided by 3EI. Okay. Now we also know that at the roller support, your displacement is equal to 0. That means your total theta B is equal to 0. Let me write it here that at roller support, B, your delta B is equal to 0. That means your delta B1 plus delta B2 is equal to 0. This will make it equal to ml square divided by 2EI plus RB L cube divided by 3EI to be equal to 0. Now in this case, what is unknown to you? Unknown is RB. So let's calculate for RB. So your RB L cube upon 3EI will be equal to ml square divided by 2EI, and that will become equal to RB will come as 3ml 3m divided by 2L. Okay, so this you will get as your reaction in this case. But in what we are interested in to determine what will be the slope at that particular point, or you can say rotation at that particular point. So your rotation will become, now you know RB, so your delta B, since delta B will not be equal to 0 at the roller support, so your delta B will become equal to, sorry, theta B will become equal to theta B1 minus theta B2. Okay, and it will be equal to, your theta B1 is equal to ml upon EI minus RL square divided by 2EI. Now substitute the value of R in this case. It will become equal to ml upon EI minus 3m L square divided by 4 EI into L. That will be equal to ml upon 4 EI. Okay. Now if you want to write with respect to m, how you will write? You can write it to be equal to, m to be equal to 4 EI theta B divided by L. But since theta B is equal to 1 as given in the question, you have to provide unit rotation. That means your m will become equal to 4 EI upon L. Okay. So this is your moment when you have unit rotation at support B. You can also say it to be a derivation of calculation of rotational stiffness when you have far end to be fixed. Like in the first, or you can say second question, we have used this concept when you have far end to be equal to hinge and far end to be equal to fits. In that condition, how we have defined the rotational stiffness. So this is how we have derived the values of rotational stiffnesses. Okay, so let's solve few more problems. So your next problem is that the support B of the following beam undergoes a downward settlement by 10 mm. Now you have to calculate the slope at the support B. What is given to you? That for the fixed end moment, clockwise moment is taken as positive, and your modulus of elasticity is 5000 kilonewton meter square. Okay, so let's solve this problem. We will solve this problem using slope deflection method. In this, delta is given to you to be equal to 10 mm. If I convert it in terms of meters, it will come out to be 0.01 meter. So using slope deflection method, so for the span AB, how you will write the equation? You will write to be equal to MAB bar, that is moment due to fixed support, plus 4EI upon L into theta A plus 2EI L into theta B plus 6EI delta upon L square. Okay, so this is the general equation for the slope deflection method. So how we will utilize this? So in this case, your MAB, so let me write here, your MAB bar is equal to 0. Why? Because there is no loading in this beam, and when there is no loading in the beam, your end moments is coming out to be equal to 0. Another thing here is your theta A will also be equal to 0. Why? Because of your fixed support. Okay, so then how your final equation will look like? So substitute in the value of MAB bar and theta A. Your MAB will be equal to 2EI upon L. So L in this case is given as 8 meter into theta B plus 6EI upon L square, that is 64, into delta, that is 0.01. Fine. So delta will become not as positive, it will be negative because it is in downward direction. Fine. Oh, sorry, I think in the formula only it is negative. I am got confused with this. So this is minus. So here minus will come. So this will be minus. No, minus will come here. Okay. So let's simplify this. It will become equal to 0.25 EI theta B minus 6 upon 64 into EI delta. Okay, so similarly for span BA, so for span BA, how you will write? So your MBA will become equal to MBA bar plus 4 times EI upon L into theta B plus twice EI upon L into theta A minus 6 EI delta upon L square. Okay. So in this case also, your MBA will be equal to 0. MBA bar will be equal to 0. Your theta A will be equal to 0. And that will give you MBA to be equal to twice EI, 4 times EI theta B divided by L. What is L? 8 minus 6 EI upon 64 into delta. And that will be equal to 0.5 EI theta B minus 6 upon 64 EI into delta. Now in this case, as support B is a roller support, so your MBA in this case will be equal to 0. Okay. So now solve this equation. That means 0.5 EI theta B minus 6 upon 64 EI into delta will be equal to 0. So solve this equation. We will get to know the value of theta. So how we will solve? We will solve it as 0.5 EI theta B to be equal to 6 upon 64 EI into 0.01. EI will get cancelled out and you will get theta B to be equal to 6 upon 64 into 0.01 divided by 0.5. Okay. If you solve it, what you will get? You will get theta B to be equal to 1.875 into 10 to the power of minus 3, and it is radians. Okay, so this is how we will solve for this and get the value of theta A. Okay, sorry, theta B. So we have calculated the value of rotation theta B. So let's solve further problems. So your next problem is you have to determine the slope deflection equation MAB and MCB for the following beam under the given loading conditions. Note, for the fixed end moment, the clockwise moment is taken as positive and EI is to be constant throughout the beam. So now your beam is loaded. It is not isolated from loading, and you have to determine the slope deflection equations for 2 points, that is MAB and MCB. Okay, so let's solve this. So here, using slope deflection method, your MAB is equal to MAB bar plus four EI theta A divided by L plus 2 EI upon L into theta B. Since there is no sinking of supports, so we are not taking it into consideration. Okay, so in this case your MBAB will become equal to, so when you have uniformly distributed load on the fixed beam, then your fixed end moment will become WL square divided by 12. Okay, that means it will be equal to 30 into 4 square divided by 12, and you will get the value as minus 40 kilonewton meter. Okay, also in this case theta A will be equal to 0 because of fixed support. So your final MAB equation, how it will look like? So your MAB will be equal to minus of 40 plus 2 EI upon L. What is the value of L? 4 into theta B. That means it is equal to minus 40 plus 0.5 EI into theta B. Now in this question, it is asked to you to determine MCB. So similarly, MCB will be equal to MCB bar plus 4 EI upon L into theta C plus 2 EI upon L into theta B. Here also you have moment at the center, so your MCB bar will become equal to plus M upon L. What is the value of M? It is 60. And what is the total length of the beam? Is 4. And it will become equal to 15 kilonewton meter. Also, your theta C will be equal to 0 because of your fixed support. And that will give you the equation MCB to be, so your MCB will be equal to 15. I have written it to be 15. Yeah. Then another thing will go off, plus 2 EI upon L. Your L is 4 into theta B. That will give you the final value as 15 plus 0.5 EI into theta B. This will be the equation for MCB. So your two equations that you want from this solution will be, this is your MAB equation, and further this is your MCB equation. Okay, now let's see what other question is telling you. So your next question is the extension of the previous question only. In this, he is telling you to determine the absolute moment value at the support A and support C of the given beam. So to determine the absolute value, we have to know first that what will be the unknown in these equations. That is, in the equation MAB and MCB, you have one common unknown, that is your value of theta B. So that means first we have to calculate the value of theta B. So how we can calculate the value of theta B? So for that, we have to first make one compatibility equation. So compatibility equation in this, what it will be, since your support B is a roller support, so you can say your MABA plus MBC will be equal to 0, because moment at roller support is always equal to 0. So now we have to derive the equations for MBA and MBC, and then we will substitute in this compatibility equation, and from that we will get to know the value of theta B, and then we will substitute in the previous torsion equations that we have derived, and from that we will get to know the absolute value of moments, that is MAB and MCB respectively. Okay, so let's solve this torsion. So again, your MBA will become equal to MBA bar plus 4 EI upon L into theta B plus 2 EI upon L into theta A. Here I have already mentioned that theta A is equal to 0, and your MBA bar, we have told it to be equal to 40 kilonewton per meter. Sorry, 40 kilonewton meter, because that will be opposite to what we have calculated previously. So this will give you your MBA equation to be equal to 40 plus 4 EI upon L. L here is 4 into theta B. That means 40 plus EI theta B. Similarly, for MBC, how we will calculate? So your MBC will become equal to MBC bar plus 4 EI upon L into theta B plus twice EI upon L into theta C. Here also we have told that theta C is equal to 0 because of its support, and your MBC bar in this case will come out to be equal to minus 15 kilonewton meter. So if we substitute the values of MBC or theta C and MBC bar, what we will get? We will get MBC to be equal to, sorry, in this case both will be positive, no one will be negative. So it will be equal to 15 plus 4 EI upon 4 into theta B. That will give you MBC to be equal to 15 plus EI theta B. Now, using compatibility equation, your MBA plus MBC need to be equal to 0. Okay, so let's substitute all these values what we have calculated earlier. So we have calculated MBA to be equal to 40 plus EI into theta B plus 15 plus EI into theta B, and it is equal to 0. And from this we got 65, 55 plus twice EI theta B to be equal to 0. That means your EI theta B is becoming equal to 55 by 2. That means minus 27.5. Okay. Now we need to calculate the support moments or absolute moments at end A and C. So absolute moments at end A and C is MAB, which is equal to minus 40 plus 0.5 EI theta B. So we'll substitute the value of EI theta B and it will become equal to 40 plus 0.5 into minus 27.5, and it will give you the value as 53.75. Fine. Similarly, if we need to calculate the value of MCB, how we defined MCB? It is equal to 15 plus 0.5 into EI theta B. That means 15 plus 0.5 into minus 27.5 to be equal to, and this value come out as minus, or you can say plus, sorry, not minus, plus 1.25 kilonewton meter. So these are the absolute moments at end A and end C respectively. Okay, so this is how you will use slope deflection methods to calculate the value of unknowns, that means this you can say rotations as well as moment at the ends. Okay, so let's solve one more problem. Okay, so your next problem is similar to the portal frame. Okay, so this is your frame in which on span BC we have a loading of 8 kilonewton per meter, and on the cantilever end in the span BD we have a moment of, sorry, not moment, a concentrated load of 20 kilonewton. So how it will become, we'll see. So in the question, it is asked to you that consider the following portal frame under given loading condition. For the fixed end moment, the clockwise moment is taken as positive. What is the absolute value of slope at theta B? So he is directly asking you that what will be the correct absolute value of slope at theta B. That means how we will calculate the slope? First, we have to define one compatibility equation. If we solve that compatibility equation, then only we can define the value of slope. So compatibility equation in this case will become, so your compatibility equation for this case will become MBD plus MBC plus MBA to be equal to 0. Okay, because it is a hinge that is provided in between, and in hinge the moment, total moment, or the summation of moment that is coming out to be equal to 0. So we need all these three moments, then we will add up, and whatever the unknown in the equation comes, that will become your slope, or you can say theta b. So let's solve for this. So first we have MBD. So your MBD is simple for you. So your MBD will become, it will give you a hogging moment. So hogging moment will be 40 kilonewton meter. Sorry, not hogging moment. It will give you a sagging moment of 40 kilonewton meter. Now for beam BC, we will use slope deflection method. So now for span BC, using slope deflection method, how the equation of MBC will look like. So your MBC will be equal to MBC bar plus 4EI upon L of BC into theta B plus twice EI upon LBC into theta C. So here theta C will become equal to 0 because of fixed support, and your MBC bar will become equal to minus WL square upon 12, and that will be equal to minus 8 into 6 square divided by 12, and that will become equal to 36 into 8 divided by 12, and it will give you the value as minus 24 kilonewton meter. So now substitute all the values in MBC. So this implies your MBC will be equal to minus 24 plus 4EI upon LBC, that is 6 into theta B. Okay, and that will become equal to minus 24 plus 2 by 3 into EI theta B. Now for span BA, for span BA, your MBA will be equal to MBA bar plus 4 EI upon LBA into theta B plus twice EI upon LBA into theta A. Here your theta A will be equal to 0. Why? Because of fixed support. And your MBA bar, what it will become? It will also become equal to 0 because there are no loading in between the span. So substitute all the values. What we will get? We will get the value of MBA to be equal to 4 EI upon L is also 4 into theta B, and it will become equal to EI theta B. Now, using compatibility equation, substitute all the values of MBA, MBC and MBD. What we will get? This implies first MBA we will substitute as EI theta B. Then your MBD will be 40. And then rest is your MBC. It is minus 24 plus 2 by 3 EI theta B. It will become equal to 0, and that will give you 5 by 3 EI theta B plus 16 to be equal to 0, and that will give us the value of theta B to be equal to, or you can say we don't write theta A, we'll write it to be EI theta B to be equal to 40 minus 48 upon 5, and it will be equal to minus 9.6 kilonewton meter. EI is kilonewton meter square and into radians. Fine. Okay, we have calculated the value of, so what it is mentioned in the question, you have to calculate the slope. So we have calculated the slope in terms of EI theta B. Okay, because EI is constant in this equation. Now your next question is, find the absolute value of bending moment at support C and horizontal support reaction at A of the portal frame given in the question number 8. So we need horizontal support reactions as well as the bending moment at the support C. So first determine all the values of the bending moments which are absolute in this case. So MBC, if we try to calculate, MBA, so MBA will be equal to EI theta B, and EI theta B, MBA we have already written it as EI theta B, and your EI theta B you have calculated as minus 9.6. Similarly, for AB, how you will calculate? So your MAB is equal to MAB bar plus 4 EI upon LAB into theta A plus twice EI upon LAB into theta B. Okay, so here your MAB bar is equal to 0. Your theta A, since the support is fixed, that is also equal to 0. Now if you substitute the values, what you will get? You will get MAB to be equal to 2 EI upon L. What is L? L is 4 into theta B. That means your MAB will become equal to 0.5 EI into theta B. So if you substitute the value of EI theta B, that will become 0.5 minus 9.6, and that will become equal to minus 4.8 kilonewton meter. Okay. So now the remaining thing is left for you is to calculate the horizontal reaction. So how you will calculate the horizontal reaction? So then let's see that. Okay. So if we try to draw the free body diagram for member AB, so let me write here that free body diagram of span AB, how it will look like. So first let's highlight what we have calculated till now. We have calculated MAB and its value is minus 4.8 kilonewton meter. Another what we have calculated is MBA and its value is minus 9.6. I will write it here. Let me remove it. I think now I will write kilonewton meter. Fine. Now what is remaining for you is the horizontal reaction. So for this, we are drawing the free body diagram of member AB. So let's say this is your member AB, and in this you got MBA equal to minus 9.6. So if you got minus 9.6, that means it will be a anti-clockwise moment. So let's say this is minus 9.6. I am writing it to be 9.6 kilonewton meter. Similarly, at end A, what you have got? You have got the value as minus 4.8 kilonewton meter. So that means that will also be anti-clockwise moment. So let's draw it to be anti-clockwise. Okay, and its value is 4.8 kilonewton meter. Now what's remaining for you is the horizontal reaction. Okay, so that means this is your horizontal reaction. I have made too big. Let me draw it again. So this is your horizontal reaction HA. Okay, so how you will calculate? You will take moment about point B to be equal to 0. So let me write here. I think I can write here only. So if I take summation of moment about B to be equal to 0, that will give me HA into LAB, that is a clockwise moment. Rest are anti-clockwise moment, that is minus 4.8 minus 9.6 to be equal to 0. That means my HA will become equal to 4.8 plus 9.6 divided by, what is the value of L? L is 4. And from this, you will get the value of HA to be equal to 3.6 kilonewton. Okay. So this is how you will calculate all the values. So I will write here the HA to be equal to 3.6 kilo Newton. Okay. So this is the problems, or these are the problems that you will solve for displacement methods. Okay, so this is how what we have solved for this current session. We started with determining what are the different methods which comes under displacement method, or you can say stiffness method. In that, we started with finding out the values of rotations using compatibility equations at different points of the frame. Then we have solved one derivation also, or you can say one question which is in the form of derivation to determine what will be the rotational stiffness when you have far end condition to be fixed. Further, we have solved problems related to slope deflection method. So we started with one prop cantilever beam having no loads, and then we increase the complexity with a fixed beam with having a roller support at the center and having two different loadings, one having a uniformly distributed load and another span having a concentrated moment at one point. We have determined how we can determine the absolute moments at the different ends of the beam. How we can do? We used a compatibility equation at the center of the beam, and then determining all the slope deflection equations and utilizing the uh, compatibility equation. We first determine the value of slope, or you can say rotation, at the support which is there at the center, and substituting the value of unknown in the given equation of the end moments, we have determined the absolute moments in the beam. After that, we have solved one problem related to a portal frame or frame in which we have not a portal frame, it is a frame. When it is subjected to a uniformly distributed load over the length of the beam in the horizontal direction. And in that, we have seen how we can determine the value of absolute moments as well as the horizontal reaction in the span AB. Okay, so this is how you will utilize the concept of displacement method and try to solve the problems which are indeterminate in nature. So we have seen how we will solve the problems related to force method. We have also seen how we will solve the problems related to displacement method. Next week, we will try to wrap up this method of, not method, we will try to wrap up this analysis of indeterminate structure. And finally, in the next week, we will see how we have introduced to you the flexibility as well as the stiffness matrix method. Okay, so in the next 2 weeks, your course will be going to wrap up. So try to ask doubts, whatever you have, in the discussion forum as well as in the problem solving session. That will help you in understanding the concepts in a better way. So if anyone has any doubt, they can ask right now. Otherwise, I will wrap up this session for today.
Sir, not any doubt.
So I think there is no question.
Yes,
So
sir.
we will meet next Saturday at the same time. Till then, solve your assignments and try to understand the concepts. Okay. So thank you everyone. Have a
Thank you,
nice
sir.
day. Enjoy your weekend.
Thank you, sir. Have a great day. Good night, sir.